It's been a while since I've done a video on blockchain, so apologies to those of you who've kind of been following this. I'm doing some other tracks on financial markets and AWS and other kind of stuff. So this is going to pick up from where we did last time. But from there, I want to kind of go on to talk a bit more about what actually makes up a Bitcoin block. So we've talked about the blockchain. This is a blockchain series. So I want to sort of start looking in more detail about what constitutes a block of Bitcoin transactions. We've seen a preview on the blockchain.info website, so I just want to go into more detail. Excuse me, I've got a bit of a cold, so excuse my voice. So we're going to have a look at what goes in a Bitcoin block. Okay, so let's get started. So here we are back at the trusty blockchain.info website, which is definitely the first port of call you should go to just to refresh your memory as to what Bitcoin transactions and what blocks look like. We saw this in the previous videos, and we saw actual examples of our own transactions appear in this console. Just to recap, that this blockchain.info is a real life snapshot of the Bitcoin blockchain. So basically, as new blocks get propagated around the network, you'll see them here. You can trace this list all the way back to the Genesis block, so all the way back to the very first Bitcoin block. And these are the latest transactions that are coming through on the network, and they will be if I just try and click on one of these hyperlinks as they come through. So I finally managed to click on one. It's quite tricky. It's like catching little fish as they swim by. So basically, so that's a sample transaction. I just wanted to show you that so this is one of the transactions that was flying by on the screen, and we can see that here we can see it's an unconfirmed transaction, right? So that means that as yet this has not been mined into any particular block. It's part of this big transaction pool that gets propagated around the network in real time and gets collected in a big pool, right? So big pool of transactions, they're coming through. So every time you go to the Bitcoin ATM and withdraw something, that's a new Bitcoin transaction. It goes over the network, it gets propagated around the network, and it ends up in this pool. Every time you buy a cup of coffee in Shoreditch in a hipster Bitcoin cafe, it's a new Bitcoin transaction. That transaction again will propagate around the network very quickly, and it will find its way into the pool of as yet unconfirmed transactions, right? So this video is going to be about basically a little introduction as to what happens to those transactions next, because obviously, as we know, they end up in a block and they end up on the blockchain. That's going to be more of an introduction though into the Bitcoin mining process, but we're going to lead from there into actually looking in detail as to what the actual block looks like, because we've already seen to some extent what the transaction looks like in terms of inputs and outputs, right? But so I'm going to go back to the main page in the blockchain info, and we're going to look at, so turn our attention to these blocks. So as you remember, so this is basically a list of all of the blocks. It actually shows the previous 6, but you can basically click more here, and you can see, you can go back as far as you want, right? And this will take you, if you want, it'll take you all the way back to the first ever blockchain, and as I think I sort of mentioned in the past, the reason why it's called a blockchain is because all of these blocks refer to each other. But I'll come to exactly how that actually, what that means later on in the video. Okay. Excuse me. So let's take for argument's sake, let's just have a look at what the most recent block in the chain is, right? So we can see here. So basically, the first thing to note about this block, which is the most recent block in the Bitcoin blockchain, is that it has a height, okay, and the height is 429,783. Okay, so basically, this is the number of blocks so far that there are in the blockchain, in the Bitcoin blockchain, right? And this is the top of the stack, right? And then so basically, we count down incrementally one by one. If you remember in our first video, we had the analogy of the guy in the back room of the bank stacking boxes on top of each other, and this was the first box and the second box and the third box, and this is basically equivalent of the, if that just points down in time, to the 429,783, right? So that's the block height. Now, the age here is 7 minutes. You can see that on average, the network is supposed to produce and propagate an official new block on average every 10 minutes. You can see that the interval between this one and the one before it was a bit more than 10 minutes. It was actually 23 minutes. And the interval between this was more like 7 minutes. But on average, you would expect to see approximately 10 minutes between blocks. Now, we'll go into why that is and where that magic 10-minute thing comes from later on in the video, or at least later on in the series. So, that's the age. So this is just basically the basic summary about those blocks. So the next one is the number of transactions, right? So the number of transactions within a block is, for this particular block, was 2,879. Really important point. The number of transactions in each block is not the same every time. It all depends on the miner who happens to successfully mine each block, and we'll come to exactly what that means again. And I know I keep saying this, but we will. So basically, that's the sort of the main metadata. You can see I guess the sort of the file footprint of the block here. They're sort of roughly just less than a megabyte, right, in terms of size. So what we can actually do now is we can just click on the home page for each of these blocks, right, and see, we can drill down into more detail about what that block was all about and what's inside it. Okay, so if we just click on this, so this is now the kind of the home page for our block number 429783. Very, very important. The hash of the block, right? So basically, so what we're saying is, once all of this block has been put together with key information about it, that block is hashed, or at least the header for the block is hashed, and that is the hash value there, right? And the header for that block includes the hash of the previous block, right? That's very, very important, and we're going to go into this when we see the actual anatomy of the block header. But so you can see that the previous block hash is this one. The hash of this particular block is this one. The Merkle root of all of the transactions is this, and we're going to go into a bit more depth about what this actually means. But if you remember, our banker, or he's not the banker, our backroom clerk from the first video, whose job was to weigh the checks in these boxes, he had to basically weigh all of the transactions together and basically and then put the checks. He was weighing checks, right? He had to put the checks inside the box and weigh that. The way it works in terms of blockchain is slightly more efficient than that, but it's the same concept. But it's all about this Merkle root here. That's the way that effectively the content of the transactions, all these 2879 transactions, are actually represented and included in the block header without actually having to hash all of the 2,879 transactions together and include that in the block header. Okay, so basically we're going to go into more detail here about what this block header looks like. And then down here on the block homepage, you can see the actual transactions that are in the block, right? And you can see, so all 2,879 of these transactions can be listed here. You can browse them all. So each and every one of these has their inputs and their outputs. You can click on each of these transactions and it'll take you to the transaction homepage for that particular transaction. So that's the block homepage on blockchain.info. So we're going to basically just go now to have a little bit more detailed look at the actual anatomy of the block header and explain how that enforces the relationship and the integrity from one block to the next. Okay. So I've drawn a little diagram here, and as always, drawing is not my strong point, but it's basically supposed to be a very crude picture of a network of Bitcoin nodes, which we talked about, I think, in the second video. So the idea is that all of the nodes on the network that constitute the Bitcoin network are all connected to each other, basically, and including my iPhone Bread wallet, so my Bitcoin wallet on my iPhone that I use to buy my coffees, is part of that Bitcoin network, and some of the nodes on the Bitcoin network are running mining software, and those are known as Bitcoin miners. Okay, so to some extent they all kind of run the same software. They all do the same job. They all validate transactions. They all propagate transactions and information about blocks to other nodes in the network. That's how we build a consensus of what the blockchain is at any point in time. One of the nodes I should also draw in here as well. It happens to be the blockchain.info website. Right? It's just another node on the Bitcoin network that keeps an up-to-date ledger of the blockchain. Again, one of the absolutely key founding principles of blockchain is that there's no centralized node. There's no golden copy of the blockchain. Each and every node on this system basically is equally responsible, is equally valid in terms of their depiction of the blockchain, but they're all talking to each other all the time, and they're all validating the transactions and the blocks that they receive, and this way a consensus is gradually built. So we saw in the previous screen, we saw these transactions flying past, right? And we talked about in real time, you can see these transactions, that they kind of build up into a pool. So if we take an example of, let's say that I go to Shoreditch, and I don't know why I always take the piss out of Shoreditch, but I guess in London it's the only place where you can really do a lot of Bitcoin transactions. So I go to Shoreditch with my iPhone, right? and I buy a cup of coffee, right, over here with my iPhone, and I pay over the counter using my Bitcoin wallet. So the transaction will first appear there, but from there it will that transaction will propagate all the way around the network, right, very quickly, like in seconds, all the way around the world to every single node on the blockchain, right? And every single node, when they receive this transaction, they will validate it. They will validate, and we'll talk about what validation means, but they'll essentially ensure that there's a valid transaction, that me buying this coffee, the transactions that I'm listing as outputs from previous transactions to spend are actually ones that I'm entitled to spend, all that kind of stuff. That validation happens everywhere, right? It happens on every node. Okay? Now the key point here is that these transactions, as they're propagated around, they don't belong to any blocks yet, right? We saw in the screen where it said unconfirmed transactions. It has not yet been included in a block. So the question is, how the hell do these blocks actually get created? Where do they come from? They sort of magically appear every 10 minutes, but how does that actually happen? Okay. Now, so I'll try and explain that now, right? And it's not that complicated, but I just want to make sure that I kind of explain it clearly. So if I repeat myself, I apologize, right? But here we go. So some of the nodes on this network are known as mining nodes, right? They're known as mining nodes. Now, what that means is that they do everything that everyone else does in terms of propagating transactions around, etc., but they do one more really important step, right? And the point is, these guys down here running mining nodes, they're trying to make money. Specifically, they're trying to earn bitcoins, and I'll show you exactly how that happens, right? It's all down to a process called mining. And essentially what happens is that as these transactions appear in real time and they get propagated around the network, right? Each of these mining nodes, they have on their computer, right, within their Bitcoin software, they have something known as a transaction pool, right? So miner 1 has a transaction pool, miner 2 has a transaction pool, miner 3, 4, they all have transaction pools of outstanding transactions that they've heard about that have not yet been included in any block, right? Don't forget that, and how do they know that? It's because each one of these nodes has a list of all of the transactions that have been included in blocks, because they all have a copy of the entire blockchain up until this point. So the blockchain includes all the blocks from the Genesis block up until the present, and then all the transactions within them, right? So when they receive these new transactions, they know that they can check very quickly that they're not part of any block, right? They're essentially they are unconfirmed transactions. So each of these, so my transaction, right, my coffee transaction, basically makes its way into the so this is the unconfirmed transactions. Okay. So it makes its way into the let's just call it transaction 1, right? And the transaction ID itself is going to be that that hash, right? That we saw in the blockchain info website, that long string of letters and numbers. But so it's going to have transaction 1 in the unconfirmed transaction pool. Meanwhile, all around Shoreditch, lots of other people are buying coffees as well, right? So let's say 2 seconds later, someone else buys a coffee, and transaction 2 gets propagated around the network, right? Like very quickly, and miner 1 and miner 2, they also, right? They have transaction 1, transaction 2. So each of these mining nodes, which is basically just a big, these days a very big kind of supercomputer, has a record. It's listening all the time for these transactions coming through, and then what these miners do is their job is really to basically group these transactions together in a batch, and basically just wrap them all up and put them in a block, right? Now that sounds very straightforward, right? As in, well, okay, so just tell me what a block looks like. So tell me what fields I need to include in it, what should be in the header, and then I just list the transactions in there, and then send it. I mean, what's so hard about that? So obviously the point is that if it was as easy as that, then everybody would be doing it straight away, right? There's no difficulty to it. So the miner 1 can basically create. You can wait until there are let's say 1,000 transactions, right? And then you can say, okay, let's just package them up, put them in a block, put them in a header, and then propagate it around the network, right? But it's not as easy as that, and I'll explain why now. Right, so I've added a few more details to the diagram. I hope it doesn't look too involved. Over here, I've just to illustrate that this is the existing blockchain at this point in time. So all these blocks have been confirmed. Instead of 400,000 odd, I've just simplified it to, let's say there's only 5 existing blocks. The dots here represent the transactions that are kind of encapsulated within each block. Okay, and the question is, where's the next block coming from, right? Who's creating it? How does it get created? So as we mentioned, right, each of these mining nodes is all the time listening for new transactions appearing on the network and putting them in this special pool, which is basically just a list of transactions that they maintain within the program. Okay, in that pool, and what they're trying to do is they are trying to produce a valid candidate to be the next block. It's as simple as that. And what we have to do now is answer, well, what is a valid candidate? Now, it comes down to this the main one thing, which is that each block in the blockchain, as we mentioned in previous videos, each block has associated with it a block hash, right? Just like in the first video, our guy who's weighing the boxes of checks on the scales, basically each box has a unique atomically accurate weight, which is basically so accurate that if you so much as change even a drop of ink on anything inside the box, the atomic weight completely changes, right? And just so this fundamental to the whole blockchain concept is that each block has a hash number or a hash string that's associated with it, which uniquely signs that block. So if anything ever changes inside that block and it's rehashed, the hash will be completely different, right? So, and then the chaining aspect of it, again, we've been over this before, but the chaining aspect of it means that each block has a reference to the hash of the previous block, right? And that reference is hashed during the current block, which means that we can't go into a block for number 5, right? So number 5, if we actually open up number 5 and see what's there under the hood, we will see, as part of block number 5, we'll see the hash value for block number 4, right? And then, you know, in turn, block 4 will contain a reference to the hash of block number 3, and that reference to block number 4 forms part of the hash for block number 5, right? So its reference to the parent block is part of the data that we hash and assign to block number 5. So the blockchain, the blockchain aspect of it is that each block is hashed, or at least each certain key fields within each block, called the block header, is hashed through this hash function, hash256, SHA-256, and then that, and part of that is a reference to the previous block hash, right? So we basically have an immutable chain of references going right the way back to block 1, right, the very first block in the chain. So with that in mind, each of these mining nodes is trying to create a candidate block to be the next block in the chain, right, to be block number 6, right? The reason they do that is because they get rewarded for doing this. They get a reward of bitcoins for doing this, and I'll talk about that when we go into more detail about Bitcoin mining, right? So let's save that to a future video. So just take my word for it. Each of these miners here are desperately they're spinning up their CPUs like anything to try and be the next miner, to basically be the person who puts that block 6 on the blockchain, right? So what does that mean? So the block is basically a data structure, like, you know, digital document. You could view it in text, or you could see a text representation of it with certain key fields in it, and then basically a list of the transactions in the block. Okay, so we need to look at the actual construct, like the actual contents of the block, to see exactly what the miner has to do here. The block has to the block that they put forward as a candidate has to follow a certain structure. It has to have a reference to the previous block hash, right? Which, by consensus, because this is the confirmed blockchain, basically everybody knows that. So the previous block hash is this value here, which belongs to block number 5, right? And so this is the first thing that basically the miner will say. They'll create a new block document, and they'll say, okay, so the previous block hash is this, right? Because it has to include that, right? And these fields are in the header. We'll go into more detail a bit later, but then they'll put a timestamp on there as well, right? Timestamp, just to say, okay, what's the current time? And obviously that keeps changing as they recalculate. Then what they do is they take this transaction pool, effectively, all the transactions that they've been assimilating, they've been collecting over the since the last block was announced, right? The new transactions that were not included in block 5, that have as yet not been confirmed, they're keeping these in a pool. And what they do is they basically take all these transactions that are outstanding, and they create a hash representation of those transactions, right? It's a representation. It's not. They don't actually take all the transactions themselves and put them through a big hash function, because that's just too cumbersome. But we'll go into that. That's the Merkle root, and we're going to talk about that later on, right? But basically, the transactions that are outstanding, they create a hash representation of them all together, right? And then they include that in the header. So basically, this purple thing here, right? This purple thing that I've put over here, this is the header, right? This is called the block header, right? And everything inside the block header is hashed, and that creates the hash for the block, right? And then the stuff that doesn't belong to the header, which is basically shipped alongside the block, or within the block, but not in the header, right? So basically, within the header, we have a few things, and they put a random number as well, right? And we'll go into why they put a random number there, okay? So they'll hash this, right? So basically, they take all the transactions that have not yet been claimed, they create a hash representation of them, deliberately sort of, being vague there, because I'm going to go into it in more detail in a second. They're going to put the reference to the previous block hash, right, which is block 5, right? They're going to put a random number and a timestamp, and they're going to basically hash all of that information together, right? They're going to put it through the SHA-256 hashing algorithm, and then this creates a block hash, right? But let's call it X, right? I'm going to move the screen up a bit. So in it, you could say, well, happy days. I mean, so we're done then. So we've created a block. We've filled out all the compulsory fields. We have the root hash for all the transactions that we're including in the block. We've listed the transactions down here, just like the transactions are listed in previous blocks. We've put a random number in there, we've put a timestamp, and we've put a reference to the previous block hash, which is block number 5. So why can't we just then submit this block to the network and say, guys, here you go, here's the next block, right? Please validate this and add it to your blockchain, right? The reason is because it's too easy, right? If that was the case, then all these miners would do it. And remember, each miner, when they're successful in terms of propagating the next block around the network and getting that block accepted by all these nodes here as the latest block in the blockchain, they get rewarded. So if it was as easy as that, it would be chaos, because it's basically trivially easy. So what happens is there's an extra layer of difficulty added to make one of these blocks a valid block, right? And it's very elegant, it's very simple, but I'm going to make sure that I hammer it home. The point is, this hash that you create here, it is required to begin with a certain number of leading zeros, right? It's really quite simple, right? So it's like saying, okay, basically just throw a dice, keep throwing a dice until you get a 1, right? But it's a similar kind of thing, but what we're saying here is that so if you're familiar with hashing, right? When you perform a hash on any document or a string or anything, you're going to get basically a completely jumbled up sequence of numbers and letters, right? It's going to, and it looks like complete nonsense, right? So basically, the point is that the chances of that hash starting with, let's say, 7 zeros are very small, right? You would have to basically just keep trying hashing something. You'd have to try hashing lots of different inputs before you get one that starts with a leading number of zeros, right? So let's just quickly have a look at an example of a previous block hash. So we're back on the blockchain site, and I'm just going to give you an example of, so we saw these already, right? So this is the hash of this block, right? And you can see, so we've got basically, it's hexadecimal representation. So we have 64 letters and numbers, letters going from A to F, right? So hexadecimal. 64 hexadecimal characters in this hash. This is the hash for this particular block number 4429783. And you can see that it starts with leading zeros here, right? So you can see here, I've just zoomed in a bit. You can see actually, so here's our block, right? We have a reference to the previous block's hash, and then this is the hash of this block, and it has 17 leading zeros, right? 17. And here's the Merkle root down there, because we're going to explain this in a second. 17 leading zeros, right? And then some letters and numbers. So basically, what we're saying is that in this example, if somebody asked you, keep running a SHA-256 hashing algorithm on a bunch of random inputs, let's say a random text file where you just change one character at a time, right? One character at a time, try the hash again. One character at a time, one hash again. And keep going until you find a hash number that starts with 17 leading zeros. So you'd be there for a long time, right? Because, well, I'm not going to go into the probabilities and maths of it, but you'd be there for an exceptionally long time. This is something that only supercomputers can do in any sort of sensible time frames. In fact, 10 minutes is what we'll see. But this is, in a nutshell, what Bitcoin mining is all about. And I was very confused for a while because when you first read about Bitcoin, you say, okay, so basically we have these big powerful computers that get rewards for solving a mathematical puzzle, and you kind of think, well, what is this puzzle, and what's it for? What do we just randomly ask these people to solve a Sudoku puzzle or something? I mean, it's not. So this is not really it's kind of a puzzle, but it's really just trial and error. It's saying, so we all know about the SHA-256 hashing algorithm, right? We've seen it in the previous video. If you haven't watched it, please watch it, because this is probably making absolutely no sense right now. But if somebody says, okay, I'm going to give you a reward when you can show me basically a hash, so you can show me an input and then a hash of that input, where the hash starts with 17 leading zeros, right? Out of 64 hex characters, right? You'd be there for a very long time. Excuse me, my throat. So, in a nutshell, we've just articulated exactly what these miners have to do, right? They have to say, right, take a batch of current, recent, unconfirmed transactions that are not appearing in any of these blocks, right? Group them all together, take a hash representation of those transactions and a reference to the previous blockchain, right? And then a timestamp, right? And then play around with this random number, and you can do whatever you want with this. It's called the nonce, right? We'll see more about it in a second. Play around with a random number and keep iterating, keep trying it. Put the whole thing through this SHA-256 hash function, and don't stop until you've found basically a combination of the random number and the transactions, basically. So a combination of all these fields, but the random number is the one that's very easy to change, right? They can basically just increment it one by one, try it. If it doesn't have 17 leading zeros in the hash, try the next one, right? Keep going, and if you are the first person out of all the miners on the network, right, and there could be lots of miners, right? I'm going to draw them all in red, and they're all competing, and they're all running supercomputers. People used to do this on their laptops, but now the competition is so fierce that you now need special. Actually, it's actually very interesting. The special hardware with the kind of the SHA-256 hashing algorithm wired directly onto the into the hardware. So it's like very specific. So you and I, we can't actually engage. Well, we can do Bitcoin mining, but we won't be successful, because the point is, it's all about the number of hashes per second, right? That your hardware can achieve, right? So basically, because all of these miners are listening to the same transactions coming in, right, over the network, and they're saying, right, keep hashing those transactions along with tweaking the random number, and basically just keep doing it as many times per second as they can until one of them hits the jackpot, right? They get 17 leading zeros in the hash, and as soon as they do that, they basically put their hand up and they say, right, guys, stop what you're doing on this block. I've actually solved this latest block, right? I have a candidate. This miner will say, I have a candidate for block 6 right now, and here it is, right? At that point, they will take the document, essentially. Think of it like a digital document. It's the new block 6. It contains transactions, my coffee transaction, the other coffee transaction, and a bunch of other transactions in the blockchain, including a hash representation of those transactions, which therefore ensures that can never be tampered with, and then it basically broadcasts that whole thing to the network, and every node of the network that receives this block will perform a validation on that block, right? And the validation is quite simple, right? First of all, it will basically validate that the previous block hash does indeed point to the latest block in the blockchain, and then it will basically look at all the transactions that have been included in the block and ensure that those transactions are also valid, right? And it will also ensure that the hash representation of the transactions is also valid, right? Now, this is very, very quick to validate, right? Very, very quick to validate. So basically, when the miner sends this block around, right, because they've managed to generate this value x, which has 17 leading zeros. So this hash will look like 1, 2, 3, 4, 5. Am I really going to draw 17 zeros? But yeah, 17 zeros, and then a bunch of other letters and numbers, and they'll say, guys, I found a valid hash that solves this block for these transactions, and please verify. And if you agree that it's valid, then please add this block to the top of your local copy of the blockchain, right? So let's say miner 1 is the first person to successfully achieve this, right? So he goes, fantastic, I've cracked it. I'm the first person in this whole network of Bitcoin miners to find by playing around with this random number here, and then playing around with the transactions that have been coming in over the network, playing around with all those details. I'm the first person of all the other miners to actually find a valid hash that starts with 17 leading zeros, and therefore I'm going to broadcast this like there's no tomorrow, and it's going to go all the way around the network, and every node basically is going to validate it, right? It goes around as quick. It propagates as quickly as the transactions are also propagating. And if you remember, each of these nodes on the blockchain, there's no centralized copy of the blockchain. Each of these nodes has their own copy of the blockchain, right? Each of these nodes, including this miner here, including this miner here, including all these ones, including blockchain info website, and including my trusty iPhone. Actually, that's depends on what software I'm running. A lot of let's leave that one out, because some Bitcoin wallets don't actually keep an entire record of the blockchain. But let's say all the nodes in the network that are responsible for propagating transactions around, they all have their own copy of the blockchain, right? And what this guy is basically saying is, I've solved block 6, right? With this, please add it. If you agree it's valid, then please add it to the top of your blockchain. So they will add it, right? And at that point, block 6, the 6th block in the blockchain, has been successfully identified. And at this point, on the blockchain.info website that we've been looking at, this is when you'll see that new block appear, because blockchain.info, which is only one node in the network that has one copy of the blockchain, they've validated and accepted that new block. So just redrawing this a bit and clearing some of the clutter. So these were our mining nodes who were connected to the network, which I've just drawn as a kind of cloud, right? So these are our mining nodes, and all the time they're getting messages about new Bitcoin transactions that are coming over the network, and they're all maintaining a local pool, right? Local pool of transactions that are coming in and some of the transactions might get to one miner before the other one. So for example, this transaction here might have made its way onto this one and this one, but not onto this one, right? So it's not guaranteed that the transaction pools across the different miners will be the same all the time. And the other point is that the miners themselves, they can actually choose which one or which of these transactions that they've been hearing about, which of the transactions to actually include in the block, right? They can actually they can decide that, and they can basically choose to choose to ignore the ones that have low transaction fees or all these kind of things. But so the point is, these miners are not forced to basically include every single outstanding transaction in the blocks that they try to calculate, right? They're free to basically do as they please, and so basically, and also it's worth bearing in mind that the transactions are coming over the wire over this network all the time, like very frequently. So basically, as they're trying these hashes over and over again, the chances are that new transactions will be added to the pool, and they can actually include the next transaction in the next hashing attempt, and that's partly because the whole hashing is basically kind of random anyway. It doesn't really matter if you don't have to kind of keep all things equal, including the list of transactions, and then just tweak that one random number. The fact is, you can add any degree of randomness, including different transactions, into your sort of input to the hash. And the most important thing is that you're just churning through as many attempts to generate this hash as you can per second, and hoping that you'll be the first person to find the hash with the 17, the magic 17 leading zeros. So I want to point out also that this number 17, it's basically it's not fixed in stone. It basically is pre-programmed to vary according to the number of miners on the network, right? So and the reason is as follows, and this is a really important thing, right? Because it all comes down to this magic sort of 10-minute number that you sometimes hear about. So the Bitcoin network will on average produce a new block every 10 minutes. Well, why is that? The reason is because by design this 17 is known as a difficulty target, right? It's known as a difficulty target, meaning the number of leading zeros that I specify here to say, guys, keep hashing until you found a hash that has 17 leading zeros. If I said to somebody, keep trying the hashing algorithm until you find one leading zero, right? One leading zero. On average, you only have to, you basically have only 16 possible values between 0 and 9 and A to F, right? Basically, so if you only have to find one, then the probability that you're going to find a leading zero on your first attempt is actually 1 in 16, right? So it's not going to take you very long to come up with a hash with one leading zero. But as you add extra leading zeros, it becomes rapidly very much more difficult. And so this number here, called the difficulty target, is designed to sort of auto adjust according to how many of these mining nodes are currently, how much computing power, how many of these mining nodes are currently competing together. And so if at such a point in time the network has loads of mining nodes and loads of computing power contributing to basically solving these hashes, this difficulty target actually goes up. So it kind of adjusts itself dynamically such that, on average, based on the computing power that's dedicated to the network at the moment, it will take roughly 10 minutes for the next hash with that correct number of leading zeros to be produced, right? So it's all very sort of clever, sophisticated in the background, but that's where that 10 minutes comes from, and that's what that's the difficulty, and it's a dynamic number, but the difficulty of finding the hash is expressed in the number of leading zeros that you're expected to produce in order to produce a valid block hash for the new block, right? And that's really the extent of the of the puzzle that we're talking about, right? So the puzzle that they're solving is simply just to find a valid hash for the new block, which contains a hash representation of of a batch of transactions, contains a pointer to the previous block, and then it basically also contains a random number that the miners are allowed to play with to help them generate the randomness to generate the different hash values, right? So that's a brief introduction into Bitcoin mining, how blocks are produced. In the next video, we're going to talk more about the sort of in-depth deep dive into the structure of a block. But I just want to sort of give you an overview of the sort of the competition element and how new blocks are created. There's a lot of material there. I know it's quite some of it's quite involved. So if you do have any questions, please leave them down below, and I will answer them. And then the next video, as I say, we'll do a deep dive into the actual structure of a block, and we'll talk about the Merkle root, how we actually represent the hash for these transactions, and all that kind of stuff. So thanks very much for watching, and I will see you in the next video.